Hello and welcome to the quest for algorithmic sight. For centuries, cartographers have charted the physical world, revealing hidden geographies and unlocking secrets concealed in plain view. But today, we embark on a different kind of cartography, a digital one. We are here to unlock the secrets of vision itself, one clue at a time. Consider the image you see before you. To a human, it is a scene, a collection of objects and ideas. But to a machine, every image is an ancient map, a vast grid of numerical pixels containing hidden stories, patterns, and profound meaning. To a computer, this map is written in an alien language, a chaotic list of numbers that holds no inherent meaning until it is deciphered. Our monumental quest is to crack this code, to teach the machine to read this language, and ultimately, to grant it the invaluable gift of sight. We are the algorithmic cartographers, and this is the story of how we will unlock the code and begin to see the digital world through the eyes of the machine. To begin our journey, we must first understand the fundamental nature of the maps we are deciphering. Our maps are not flimsy paper and ink. They are robust, multi-dimensional data structures known as 3D tensors. Every digital image is defined by precisely three core dimensions. The first two are straightforward: height, representing the vertical number of pixels, and width, representing the horizontal number of pixels. These define the flat surface area of the map. But the third dimension is the key to color and depth of information. This is the channels dimension. Channels are the distinct layers of information stored at each pixel location. A standard color image, like the ruby gemstone shown here, has three channels: red, green, and blue. If you were to look closely at the data structures on the right, you would see that the red channel contains one set of numbers, the green channel holds another, and the blue channel holds a third. When these three layers are combined, they produce the full spectrum of color we see. The key takeaway here is critical. To understand the image, to grant the machine sight, we must learn to interpret the numerical patterns hidden across and within these channels. To find a specific pattern within this dense numerical landscape, we need our first essential tool. We call this tool a cipher key, though in the technical parlance of deep learning, you may know it as a filter. The Cipher Key is a small, specialized processor designed to look for a very specific recipe of channel values at any given location. Let's use the example of the crimson detector. Imagine we are searching for a pure crimson ruby within the input image. What is crimson's recipe? It is characterized by high red intensity, combined with very low green and very low blue intensities. Our Cipher Key is therefore armed with three corresponding weights. We assign a high positive weight to the red channel, +10. Conversely, we assign negative weights to the green and blue channels, -0.5 each. When this key is applied to any pixel, it calculates a score based on a weighted sum of the underlying red, green, and blue values. A high positive score signifies a perfect match for the recipe. We've found our ruby. This process, simple as it sounds, is the fundamental building block of algorithmic sight, and is structurally identical to how a single artificial neuron calculates its output. A single cipher key, applied just once, reveals only one location where our feature might exist. But to chart the entire territory, we must perform a systematic search across the entire map. This operation is known as the grand scan, or mathematically, convolution. The process is straightforward yet incredibly powerful. We sweep the cipher key over every single pixel of the input map, one small step at a time. At each new location, the key calculates a score, telling us how strongly the target feature is present there. All these scores are then compiled into a brand new map, which we call the clue map or the feature map. This clue map highlights where our target feature exists. The bright spots correspond to the high scores where the crimson ruby was successfully identified. Here is a crucial insight. The very same cipher key and its specific weights are used for the entire scan, across every location. This ancient and efficient technique, known as weight sharing, is what allows our system to find a pattern everywhere using just one highly specialized tool, making the grand scan both comprehensive and computationally efficient. So far, our keys have focused primarily on detecting color recipes. However, many secrets are not held in a single point, but rather in the shape and contour of the landscape. For this, we must evolve our tools. We introduce expanded cipher keys, often called spatial filters. Instead of looking solely at the color values of a single pixel, these expanded keys examine a neighborhood of pixels, such as a 3x3 grid. This area is the key's footprint, known as the local receptive field. By meticulously designing the weights within this footprint, we can create keys that detect fundamental shapes like horizontal lines, vertical edges, and corners. For example, consider the vertical edge detector shown here. It has high positive weights on the left, +1, zeros in the middle, 0, and negative weights on the right, -1. When this key scans an image, it produces a high score only when it crosses a sharp transition from light to dark or vice versa. Applied to a satellite view of ancient ruins, this key produces a high score when its center aligns with a vertical wall, revealing the structure's hidden layout in the resulting clue map. This expansion into spatial analysis is a massive leap forward in granting the machine geometric understanding. Let's demonstrate the power of the Cipher Key as a pure pattern matching device. The keyhole cipher, shown in panel A, is a carefully designed template for a specific symbol we wish to locate. When we scan the input map, B, with this keyhole cipher using the grand scan, the resulting clue map, C, gives us a probabilistic view of where the pattern exists. The brighter the pixel in the clue map, the better the match between the image pixels and the key's template weights. Crucially, a perfect match, where the input pattern aligns flawlessly with the key's structure, yields the highest possible score. To isolate these perfect discoveries from the weaker matches, we apply a mathematical boundary or a threshold. Any score below the threshold is set to 0, black, and high scores remain white, yielding the thresholded map, D. This definitive map confirms the exact locations of the feature. Ultimately, the system has successfully identified every instance of our order's hidden symbol, E. This capability is the essence of feature extraction, turning a complex visual puzzle into a clear, marked map of specific instances. As we advance in our quest, we face a critical obstacle inherent to our current system: the shifting sands of reality. Our existing cipher keys, effective as they are extreme perfectionists. They look for features only in exact, specified pixel locations. But the real world, and indeed our maps, are rarely so pristine. What if a clue is slightly shifted? Imagine a misprint in a scroll or a stone displaced by just 1 pixel in a mosaic. If a feature is even a fraction out of place, a rigid cipher key will fail to report a match, or, at best, report a very weak one. This extreme sensitivity, while good for detecting perfect alignment, means our system lacks robustness. If we want our algorithmic sight to function in the dynamic, imperfect reality of images, our methods must become resilient. They must find the core pattern even when it is not perfectly aligned or is slightly displaced. How do we grant our keys this essential tolerance for imperfection and shift? This demands a new technique to generalize the discoveries made by our filters. The solution to the problem of rigidity comes from the masters, who taught us a technique called pooling or downsampling. The core idea is simple. Instead of examining every granular detail of our clue map, we summarize the territory to maintain the knowledge of what was found while relaxing the requirement for where it was found. Specifically, we use max pooling. We divide the map into small, non-overlapping blocks, typically 2x2. For each block, we only keep the single strongest signal, the maximum numerical value found within that quadrant. The benefit is profound. This summarization tells the next stage of our system that a feature was found within a certain region, without needing to know its precise coordinates. This grants us shift invariance. Our system can now recognize patterns even if they are slightly displaced or shifted by a pixel or two. A critical bonus of this technique is efficiency. By summarizing, we make our clue maps smaller, drastically reducing the data volume and allowing the rest of the quest, including subsequent grand scans, to proceed faster and with greater focus. While pooling grants us resilience, efficiency is paramount in the grand scale of algorithmic mapping. Instead of performing a standard grand scan over every single pixel and then running a separate pooling step to summarize, we can do both simultaneously. This optimization technique is called striding. In a normal scan, our cipher key moves 1 pixel at a time, known as a stride of 1, resulting in a large output map. Striding, however, allows us to command the cipher key to take larger, deliberate steps, or strides. For example, a stride of 2 means we move the key 2 pixels right and 2 pixels down for the next calculation. By taking these larger steps, we evaluate far fewer positions on the input map, directly producing a smaller, summarized clue map. Strided convolution is therefore a more elegant and faster journey to the same general destination. It effectively combines the feature detection of the grand scan and the dimension reduction of the summary into a single, highly optimized operation, accelerating our entire deciphering process significantly. Up to this point, our artifacts have been relatively simple, a 3-channel RGB image. But in reality, as we move through the hierarchy of our system, our maps rarely remain simple. Clue maps generated by previous stages can possess dozens or even hundreds of channels, representing countless detected features. Deciphering these multi-layered artifacts requires an extension of our cipher key concept. This leads us to the crucial rule of the order. A cipher key must always have the exact same number of channels, or depth, as the map it is currently deciphering. Therefore, a standard 3x3 spatial key designed to scan a 3-channel RGB map is actually a 3x3x3 block of weights. When this volumetric key is applied, it processes all input channels simultaneously. The weight in the key that corresponds to the red channel interacts with the red pixel value, the green weight interacts with the green pixel value, and so forth. All 9 values from the red channel, plus all 9 from the green, and all 9 from the blue are combined into a single weighted sum. This effectively collapses all the layered input information into a single score, thus producing a single-channel clue map as the output. This capability is vital, allowing us to analyze deep, rich feature volumes produced by the preceding layers. No single clue or specialist can solve a truly complex puzzle. To decipher intricate maps, we must move beyond individual keys and deploy an entire collective, which we refer to as the Guild of Decoders. In algorithmic terms, this collective is known as a convolution layer. A convolution layer is defined as a collection of many different cipher keys applied simultaneously to the same input map. Each key in the guild is a specialized detector, searching for a distinct feature. For example, Cipher Key 1 might look only for vertical lines, Key 2 might be specialized in detecting red curves, Key 3 targets a specific fine-grained texture, and Key 4 seeks a certain swirling pattern. Since every specialist operates independently, each one produces its own unique clue map based on its specific focus. The result is a new, complex output map where all these individual maps are stacked together. This creates a richly detailed, multi-channel output map, where every decoder in the guild contributes one channel to the new feature volume, providing the next layer with a comprehensive, nuanced understanding of the input's components. The ultimate secrets of vision are not found in one powerful step. They are revealed through a carefully constructed hierarchy of secrets. This hierarchy is the backbone of our system, where each successive layer builds upon and refines the discoveries of the last. The final challenge before us is the most complex yet, deciphering the royal coat of arms. This elaborate symbol cannot be located with a single cipher key, as it requires contextual understanding of its components. We must therefore build a layered system that learns its structure, moving from the simplest lines to the final, majestic form. Layer 1 will be responsible for finding the most fundamental primal shapes, the individual lines and curves that constitute the image. Layer 2 will then take those primal shapes and assemble them into meaningful symbols, such as the recognizable form of a crown or the head of a lion. Finally, Layer 3 will analyze the placement and context of those symbols to recognize the complete arrangement, the entire royal crest. This hierarchy is how our machine learns to see complexity. We commence with the foundation, Layer 1, tasked with etching the primal shapes. Our first guild of decoders scans the raw input map, the royal coat, which is merely a collection of pixels and color channels. Their task is purely foundational. They are not trying to find an object like a lion or a crown, but rather to identify the most fundamental patterns that form them. These specialists are the edge and curve detectors. They are keys for horizontal edges, vertical lines, diagonal slopes, smooth curves, and simple textures. Once the grand scan and pooling steps are completed, Layer 1 produces a rich, multi-channel clue map, shown on the right. Map 1 is a map of where horizontal edges exist, Map 2 shows where vertical lines are present, and so forth. This output map, a volume of fundamental geometric discoveries, then becomes the input for the next, more abstract layer. We have successfully broken the image down into its basic visual alphabet. Moving deeper into the hierarchy, we arrive at layer 2, assembling the symbols. This second guild no longer interacts with the original low-level pixel map. Instead, it analyzes the clue maps, the primal shapes map, created by layer 1. This layer searches for patterns of patterns, establishing meaningful abstract concepts. The specialists in layer 2 are detectors for specific symbols. For instance, a layer 2 key, which we call the crown detector, might learn that a crown is a specific arrangement of horizontal lines and small curves, which were detected in layer 1. Another key might learn that a lion's mane is a collection of radial textures and specific curves. The output of layer 2 is a new, much more abstract clue map. Its channels no longer represent simple, foundational elements like horizontal line found here. Instead, they represent complex, symbolic concepts, such as crown found here or shield shape found here. We have successfully transformed geometric elements into recognizable components. We reach the final stage of understanding in layer 3, revealing the royal crest. This final guild consists of the master decoders. Their input is the symbol map created by layer 2, a map which already confirms the presence and location of the crown, shield, and lion components. These master keys analyze the relationships between the symbols to make the final judgment. Their specialist key, the forward-facing coat of arms key, looks for the expected arrangement. A crown placed above a shield, flanked symmetrically by 2 lions. Because the data has been extensively downsampled and summarized through previous layers, this final filter is typically large enough to cover the entire remaining map. The final verdict is then produced as the ultimate output. A single, strong signal from this key, represented by a bright spot in a 1x1 map, means we have successfully identified the royal coat of arms in the correct arrangement. The quest for this particular secret is officially complete. The machine has gained true conceptual recognition. This visual diagram represents the complete architecture of our quest, the cartographer's complete blueprint. It shows a powerful cascade of convolution and pooling layers that transform raw pixels into profound conceptual understanding. We begin with the input map, perhaps 12x12x3 in size. Layer 1 performs primal shape etching, applying many specialized keys, followed by pooling, resulting in a feature volume that is smaller in area but deeper in complexity, perhaps 6x6x4. Layer 2 then takes this output, performs symbol assembly, further condensing the information and increasing the level of abstraction, resulting in a smaller volume, perhaps 3x3x3. Finally, layer 3 focuses on crest identification, reducing the map down to a single location, often 1x1x2, where 2 might represent the 2 classes, yes or no. Every layer in this architecture operates at a higher scale of abstraction than the last, successfully building complex understanding upon the foundational discoveries of edges and curves. This blueprint is what we call a convolutional neural network, or CNN, and it is the key to algorithmic sight. We have successfully concluded our quest and revealed the foundational secrets of machine vision. We have learned to wield 4 central techniques to unlock the code. We utilize specialized cipher keys, filters, to detect specific patterns, from colors to complex edges. We employ the grand scan, convolution, to systematically chart entire maps of features, leveraging the efficiency of weight sharing. We mastered summarization, pooling, and striding to find clues robustly, regardless of minor shifts or misplacements. And critically, we constructed the hierarchy of secrets, the multi-layered CNN, to build simple, primitive discoveries into complex, contextual understanding, allowing the machine to recognize symbols and arrangements. The treasure we sought is not gold or jewels, but something far more valuable: the wisdom to construct these elaborate hierarchies, to teach a machine how to see the digital world, and, in doing so, to unlock the hidden stories contained in plain sight all around us. Thank you for joining the algorithmic cartographers on this journey.